All right. Hello, everyone. It is my pleasure to welcome you to our second session of S3 seminar series. And today, it's my pleasure to introduce to you István, who is going to tell about the Cambrian explosion of private message detection schemes. And don't forget to turn on your microphone.
Is it not turned on? Not yet.
Is it muted?
I don't know. Can you hear me, or it's the same? No. Okay.
Try again.
Is it better now?
I hear you, but not with a microphone.
Okay. Thomas, help us. Okay. Sorry. So maybe now it's better. So today I would like to talk about private message detection schemes. Thanks, Thomas. This talk is based on works with Alessandra, Varun, Omer, Denis, Balázs, and Péter. So my name is István, just for you. It's Esteban in Spanish. I'm a fourth-year PhD student at Eötvös University. I'm only here for a limited amount of time, unfortunately, but you're more than welcome to come to Office 236. It's a nice composite number. Anytime. Would like to get to know you and talk about what you are interested in and what problems or questions you might have. And yeah, okay. So what is the problem I would like to talk about today is the problem of recipient anonymity. So imagine there's a table, and on this table there are a lot of ciphertexts or messages incoming. And so this is gibberish. These are ciphertexts, you don't know what it is. They are just keep coming because people are using the payment system, let it be a privacy preserving payment system or a recipient anonymous messaging system. And the problem is that as a recipient or as a user of this system, you would like to find which message is meant to be received by you. So which message is for you, and you want to find it in an efficient way. So this is what you see. And with some cryptographic magic, what we want is that you should see something like this. Like you can immediately see like, that's my message. That's what I want to read. But this is hard because now on this table, on this, you only see gibberish ciphertexts. So why do we care about metadata-resistant communication in general or recipient anonymity in particular? So let me just go back in time 20 years. After 9/11, the US accepted the Freedom Act, and they authorized the NSA to record and collect every phone call in the US. And they were saying that you shouldn't worry, guys, because we don't record the content of the phone calls. But we only record metadata of the phone calls, namely who you call, when you call, for how long. And the argument was that you don't need to worry because it's not that much of a big privacy leak because we don't record what you are talking with your wife, with your girlfriend, boyfriend, whatever. We only just record metadata. But as it turns out, like a few years ago, there was this famous sentence from Michael Hayden, former president of the NSA. We kill people based on metadata. So already metadata is super rich source of information that allows us allows the NSA, the FBI, and the CIA, and other nice three-letter agencies to know a lot of information about targets. So we really need to care about metadata-resistant communication, in particular recipient anonymity, because people's lives depend on it. Okay, so what are the immediate ideas, what we could do? So we could download all the messages from a blockchain or from a store and forward system. And this is private because the server doesn't know which message you are interested in. You downloaded all the messages, but it's inherently slow, like these cute rabbits that are running around the campus. So the other idea, like obviously you don't want to download the whole blockchain, you don't want to download the whole database, so this solution is wasteful in terms of bandwidth. The other immediate idea is that you ask the sender that, hey, whenever you send a ciphertext to the server, attach my public key to the ciphertext, and then whenever I go to the server, I authenticate myself, hey, give me all my messages that correspond to that specific public key. So basically, this is the give me mine strategy. This is not private. The server will know that which are the messages that are sent to you, but it is obviously super fast, like this nice leopard. Okay, so what we really want is what would be an ideal message detection scheme. It incurs sublinear bandwidth cost for the recipient. So we don't want the recipient to download the whole database, which could be a blockchain, which is basically a public bulletin board, or it could be a store and forward server for a instant messaging application. And we want a privacy enhancing respecting solution. So the server should not know anything about whatsoever which messages the recipient is interested in. What are the applications? Where recipient anonymous messaging, privacy preserving light clients for privacy respecting cryptocurrencies like Monero, Zcash, privacy overlays. So for example, you can imagine that you go to Ibiza or Mallorca for a week, you are offline for a week, you arrive back home and you want to check whether there's a payment occurred on the blockchain that is sent to you. Meanwhile, you were enjoying the sun on Mallorca. And you don't want to download the blockchain that occurred in that 1 week, but can we come up with a better strategy to detect the message that was sent to you? So these two are messaging applications. Note that Signal only provides sender anonymity, not recipient anonymity. Recipient anonymity is notoriously hard to provide in an effective way. Catch is a new messaging application developed by Sarah Jamie Lewis, and these are cryptocurrencies that could benefit from this cryptographic scheme. Okay, so I would like to this talk will have 3 parts. In the first part, I will just overview the 3 recent papers, 3 recent protocols, and then I will mostly focus on fuzzy message detection, FMD for short. And then I will talk about I will give you a privacy analysis of this FMD paper, which is our most recent work. And then hopefully we will have some time to chit chat questions, but please feel free to interrupt me anytime, because most likely if you don't understand something, it's not you, but it's me. So we are here to learn from each other. So let's take advantage of this. So yeah, please feel free to interrupt me anytime, even if you are on Zoom. Okay, so let's have an overview of the solutions we have so far for this problem. Let's digest this slide. It might be too much, but let's go row by row. So we already discussed the naive scan. This is the download them all strategy. It provides full privacy, but the recipient and the server needs to do all the big O of M work. M is the number of messages. So if there are M messages, then the recipient needs to download all the messages, and also the server needs to give all these messages to the recipient. But it doesn't require any cryptographic or any other assumption. And the focus of this talk is a really nice paper by Gabriel Beck et al. It's called Fuzzy Message Detection. It doesn't provide full privacy. It provides K anonymity style guarantees, where K is proportional to P times M. P is a really crucial parameter. P is a number between 0 and 1. It's called the false positive rate. I will talk about it more a little bit later. So the recipient needs and the server needs to do big O of P times M work. And note that there's a tension between privacy and efficiency. So the larger is P, the more privacy we will have, because K is proportional to P times M, but also the more work the recipient and the server needs to do. And the closer P is to 0, the less privacy have, but the scheme will be more efficient. So it seems that this paper might give us a nice trade-off between efficiency and privacy. And it assumes this paper is proven, this protocol is proven to be secure under the computational Diffie-Hellman assumption. The most recent paper is a work by Liu and Tromer from Tel Aviv University. It's called Oblivious Message Retrieval. It provides full privacy. It is post-quantum secure because it assumes the ring learning with errors problem. And it is a really beautiful paper and asymptotically really interesting protocol because the recipient now only needs to do logarithmic work. And the server still needs to do linear work in the number of messages. But practically, this scheme is not efficient because the detection key of the recipient is like 1.2 or 1.3 gigabytes or something like that. So interesting construction, but not super practical. And then a joint work with Varun, Madathil, Alessandra, Scafuro, Omer, Shlomovits, and Denis, Varlakov. We call this protocol private signaling. It is even more interesting from an asymptotic point of view because the recipient needs to do constant work in both of our protocols, and the server needs to do linear work. But the not so nice thing or the drawback of our protocol is that in one case we assume trusted execution environment, which is might be too much of a assumption in protocol or in protocol design. So it's kind of cheating, and we all know that how vulnerable trusted execution environments are. And we know all these papers where they manage to break the confidentiality guarantees of TEEs. So it's not something, it's too much of an assumption. And the second protocol we propose in the paper relies on two non-colluding servers. So in practice, it's also might be too much of an assumption. So basically, the takeaway message from all this little overview is that so far we don't have a silver bullet. We don't have a solution that could be used right away because either they require too much privacy assumptions, trusted execution environments, or two non-colluding servers, or they are just not non-practical. And so my focus in this talk is to analyze fuzzy message detection from a privacy point of view, because this is the scheme which is most efficient from a practical point of view. Yeah, sure, please.
So here, like, there are M messages, I understand, right? But I don't really understand what it means when you have O of one computational effort for the recipient, because does that mean that it doesn't need to read all the messages, or?
No. It doesn't need to read the messages. That's the beauty of those protocols.
Okay.
So they are really simple protocols. So maybe let's take this discussion offline.
Yeah.
But it's really not, I wouldn't say it's trivial, but it's not super difficult to understand them.
Sure. Okay.
But we need to assume trusted execution environments, and for the second protocol, we need two non-colluding servers, which in practice might be hard to instantiate, to find two parties that will promise us that they will not collude. Ada? Maybe you...
They were saying that there are companies that are offering...
No, that's the correct.
It's not even really a question, it's more of a comment. They were saying that there are companies, I think it was IBM, that offer to be a second server as a service. So you could be able to implement this between your company and this second server as a service.
Wow, that's nice. I will let my co-authors know. I didn't hear about this, thanks.
I have one question about the recipient privacy that you are considering here. You want to hide which message you are retrieving and who you are, or you want to make sure that the server doesn't know, like, this message arrived for this public key or not?
Or the later. Yeah. So basically, we want to hide the fact that a specific message was sent to you. Because I don't know, you might be a journalist in Afghanistan, and okay, so we know all these use cases we are interested in. Okay, so this was a little overview of the current solutions, and this is an open question to all the cryptographers and everyone here. Like, let's come up with something which is practical and still provides full privacy, because we don't have such a scheme. So it would be nice to come up with something meaningful here. Nikita?
There is a question on Zoom. If the table lists the receiver-server computation, what is the communication complexity?
Between the server and the recipient? It's not on the slide. this slide is really oversimplification, I admit, but it's on purpose. I omitted a lot of logarithmic factors, and also I didn't show the communication complexity between the recipient and the server. Most of the time, so these two are in our paper, it's basically constant, but in the garbled circuit construction between the two servers, they need to talk big O of M, but usually the recipient and the server needs to talk so not that much, only constant. And in fuzzy message detection, since you download P times M messages, basically it's linear in M. I mean, it depends on P, which is a false positive rate, but I will get back to that in shortly. Okay, so let's talk about fuzzy message detection in a nutshell. So fuzzy message detection is a new cryptographic protocol proposed by Gabriel Beck et al. It consists of 5 polynomial time algorithms, a setup which outputs public parameters, a keygen which outputs for the recipient a public and a secret key pair. And there is a flag algorithm which is probabilistic, and given the recipient, the sender runs this, given the public key of the recipient, it outputs a flag ciphertext, and the sender will send this flag ciphertext with the message to the server. And now the recipient can extract, given her secret key and the false positive rate P, which is a number between 0 and 1, the recipient can obtain a detection secret key. The recipient will get this detection secret key and sends it to the server. Now the server, the last algorithm, the server, given the detection secret key obtained from the recipient and the flag ciphertext obtained from the sender, can test whether a flag ciphertext will give a match with respect to a detection secret key. So a match corresponds to that this algorithm outputs 1. Okay, this is a toy example. So we have a small universe of senders. We have 4 messages, a yellow, a blue, orange, and the white message. And here we have a server, and we have 4 users. And so each user defines their false positive rate. For example, recipient A defined false positive rate 0, which means that recipient A will only download the message which was sent to her. So in this case, the orange message was sent to recipient A. Therefore, recipient A will only download this specific message and none of the other messages. Recipient B and C, on the other hand, define their false positive rate to be 1/3. So it means that they download their true positive message and they download one of the 3 remaining messages. And lastly, recipient D is a super privacy cautious user. Recipient D defined his false positive rate to be 1. It means that he downloads his own message, which was sent to him, and also all the rest of the other messages. And the interesting thing, which you should note, is that now the server knows, I mean, recipient A downloaded only 1 message, and his false positive, the server also always knows the false positive rates of all the recipients, but I will talk about the system and the threat model in a bit. So now the server surely knows that recipient A received the orange message, and the recipient B or C received either the yellow or the blue message. So recipient and B and C enjoys 2 anonymity because their message's anonymity set is 2. But even though recipient D did the most of the job, now still the server can deterministically link the white message to the recipient D. So it's like the takeaway message from this slide is that there are, this type of privacy guarantee is called interdependent privacy, where your privacy guarantees depend on what the other players do. So even the recipient D does a lot of work, he downloaded all the server, all the content of the server, of the blockchain or store and forward server, still he doesn't enjoy any privacy. So this is counterintuitive, but this is just to convey the idea that fuzzy message detection is not, it's always not super nice if you don't provide full privacy, because something fishy can always go under the hood. Okay, so what are the security and privacy requirements in an informal way? So we let's say there's Alice, and Alice received 3 messages. These are denoted as green dots, and there are other 5 messages which are denoted as red dots. So correctness dictates that Alice always needs to download all the true positive messages. So Alice will always download the green dots because those messages were sent to her. Fuzziness means that for every message that was not sent to Alice, Alice will download those messages with probability P. So for every message, there's an independent probability P that Alice will that specific flex ciphertext will give a match to Alice's detection secret key. So we call this property fuzziness. I just give the intuition of the security requirements. And the last property we want from a fuzzy message detection scheme is detection ambiguity. So the server should not know, given a match, whether it's a true positive match or a false positive match. It's nice because this means that all the false positive messages can act as a cover traffic for the genuine messages. So these are the security and privacy requirements we want from a fuzzy message detection scheme. And in the paper, Gabriel Beck, Julia Len, Jan Myers, and Matthew Green, they provided 2 nice instantiations. One is based on the hashed algamal encryption scheme, and it has super small flex ciphertexts that only contains 2 group elements. And then there's another construction which is based on garbled circuits, and that has largish flex ciphertext. So that one is not super practical. It's a really nicely written paper. A personal confession is that this year, this might be my favorite paper. I really enjoyed it, and it motivated me to work on this problem. So I really encourage to other cryptographers or everyone interested in this area to read it, because it's really nicely written and it's really nice. Okay. So what is the appropriate false positive rate? That's the crux of this. So when this scheme was posted on ePrint in January, February, there was a lot of fuzz about this paper, pun intended. So there was a lot of fuzz in the cryptocurrency community that this is something super interesting. We need to integrate it into our cryptocurrency. We need to integrate it into our wallet scheme. We need to integrate it into our messaging application. But developers, I saw all these PR, GitHub issues and GitHub requests or discussions but we don't really know how to implement it, because there's this magical false positive rate, and it's really non-trivial how to choose this parameter that it will respect the user's privacy. Okay, so, and then we ask the question, okay, how do we need to choose this false positive parameter? And then we will find out that why fuzzy message detection leads to fuzzy privacy guarantees. So what is the system and the threat model? Well, we have a sender or a universe of senders. They post recipient anonymous messages to a message board, which can be a public bulletin board, which can be a blockchain, which can be a store and forward system. And then there's a server who does the message filtering for the recipients. So the recipients are intermittently connected, maybe once in a while, once in a week, so they are not always online. And they would like to receive their messages or payments from the server in a recipient anonymous way. So what is the threat model? What are the adversaries we are considering? So the adversary's goal is to learn as much as possible about senders, recipients, the messages, and their relationships. So who sent to whom and which message. The server obviously is our biggest concern, because the server can inspect all the messages, flex ciphertexts. It can carry out whatever analysis it wants. And it's also not an unrealistic assumption to assume that the server also knows the false positive rate of each user. But obviously the server cannot break crypto. And we have an eavesdropper who might observe the amount of data that is downloaded from the server. For example, an internet service provider can do such a thing, and we will see later why it is bad that even if you just see the amount of downloaded data, because it can reveal how much genuine messages you received. So this is a slide just to quickly describe the notations we use. the number of honest users is U, the number of messages is M, but I will remind you anyways when we will have the formulas, and you will not forget which variable corresponds to which notation. Okay. So the way I like to think about this problem, this is my mental model, is basically a bipartite graph. So in one of the classes of the nodes, there are the messages on the left-hand side, and on the right-hand side, we have the users. And basically the server sees this, and between two nodes in this graph, there's an edge if that specific message was downloaded by that specific user. So, and I denote with red arrows the messages which are true positive matches, and I denote here with green arrows the messages which are false positive messages. They are just downloaded for the sake of cover traffic. And the server essentially wants to figure out the color of each edge. And in this example, let's say user 1 defined her false positive rate to be 1. So it means that she will download her message 1 and all the other messages, because he will download everything. Let's take another example. For example, user 2 defined her false positive rate to be 1/2. So since message 2 was sent to user 2, she will download message 2. And with probability 1/2, she will also download message 1 or message 3. In this case, message 1 didn't give a match for the detection secret key of user 2, but message 3 gave a match. So user 2 will download that message. And as a last example, for example, user 4 defined her false positive rate to be 1/3. She did not receive any message, but still she will download a message, message 1, because she defined her false positive rate to be 1/3. So this is just a small toy example to give you some intuition what's going on. So let's start with an information-theoretic privacy analysis. So what are the privacy guarantees we want to obtain whenever we are considering a anonymous communication system? One of the cornerstone probabilities we care about is called recipient unlinkability. Recipient unlinkability says that given two messages, it should be indistinguishable that the two messages were sent to the same user or to different users. And in fuzzy message detection, this is not the case because we can easily differentiate between these two worlds. Why? Imagine the following adversary. So if the two messages were downloaded by different sets of users, let's say message 1 is downloaded by Alice, Bob, and Carol, message 2 is downloaded by Dave, Eve, and Frank, then you are sure that these two messages were received by different users. And the simple adversary strategy, on the other hand, if there's an intersection of these two sets, it will just guess that, okay, most likely this will be downloaded by the same user. Let's quantify the adversarial advantage. And I'm glossing over the details. It's not really important. It's like super similar computation. If you know the birthday paradox, it's something really similar where you have two sets and you want to compute whether these two sets have an intersection. And at the end of the day, we will end up with a negligible function. But note that this is, so the textbook recipient unlinkability definition says that we want this advantage to be negligible in the security parameter. And here what we have is that this is a negligible adversarial advantage, but in the number of users. So basically what it says that recipient unlinkability only holds if we have a lot of users in the system. And for certain scenarios, we computed the correct and precise values of the adversarial advantage. The other property we care about is relationship anonymity. So the server should not know who is communicating to whom, right? And observe that if there's a lot of messages with the recipient, so if a sender between two nodes, if there are a lot of messages, then it might be statistically detectable that something, it's not coincidence that there are many downloaded messages from that user. So the number of messages that the fuzzy links, we just call it fuzzy link in this graph, that was received from V to U. It follows a binomial distribution with parameter out V. So every sent message of V, there's a probability PU that recipient U will download that message. And this binomial distribution can be well approximated if the product of these two parameters is large. As a rule of thumb, statisticians say that it needs to be at least 5, and then this approximation is tight. So we can approximate this binomial distribution with the normal Gaussian distribution. And so basically what we want to test, whether this number of fuzzy tags in the graph could come from this normal Gaussian distribution. And we can test this with z-tests or students' t-tests. And basically what we computed is that given the number of sent messages of a sender and the recipient's false positive rate, what's the maximum number of messages they can exchange in a way that statistical tests will not detect it. And let's take an example. So if the sender sent 1,000 messages and the recipient's false positive rate is 0.3, then they can exchange at maximum 54 messages. If there's more than 54 messages, then the statistical test would reject the hypothesis that this number could come from this distribution, and then the server will be able to say that, hey, they surely exchanged a message. Okay, so basically this hints that fuzzy message detection might not be applicable in applications like messaging, because if you use WhatsApp or Telegram, then surely two people exchange a lot of messages in a certain time interval. The last property we cared about is called temporal detection ambiguity. Or deniability. Some people use this term. So it means that the server should not know that someone received a message in a time interval. So, and the number of messages in an interval follows, again, a binomial distribution with parameters m. So for every message m, there's a probability pu that that specific message will be downloaded by recipient u. And so the intuition is that imagine that you go to a restaurant with your friends and you settle the bill. And after you go out from the restaurant, all your friends will pay you what you paid. So in a certain time interval, you will have a lot of incoming payments or messages. And such interval can be suspicious because all the rest of the days you have, so if you have a look at this histogram of the yellow this yellow histogram, then you will see that this is taken from a real communication network. So between these 2 months, this guy or girl received a lot of messages, but on the other hand, in the rest of the week or month, she didn't receive that much messages. And so this can be suspicious, and you can test this, whether this is coincidence or not, again, with z-tests or standard statistical tests. But on the other hand, if we raise the false positive rate of this user, then we can mask these suspicious time intervals. And now the question is, like, what should be the smallest detection rate such that it defeats statistical tests? And we computed it for many parameters. Let's take a few examples. So for example, if in the system there are 1 million messages and the user receives 1,000 message, then it should have at least 0.13 false positive rate in order to be able to deny that it received a true positive match in this time interval. Okay, now let's talk a little bit and have a look at fuzzy message detection from a differential privacy point of view. How many of you know differential privacy, or who doesn't know anything about differential privacy? Okay, so differential privacy is the most used privacy guarantee on the Earth, on the planet. US census data will be released in a way that is protected with differential privacy. So census is like when some strangers go to your home and ask, like, what's your height, what's your weight, what's your religion, sexual orientation. So they ask a lot of confidential stuff. And this US Census Bureau decided to release all this data, but obviously they cannot release it in a clear text because that would violate the privacy of a lot of users, and it would be really easy to re-identify the users. So they decided to do this in a way that they protect all this data with differential privacy. And this is like the data of 330 million people. So it's really powerful that they released it, because it will be super useful for many scientists around the globe. So basically, just intuitively, differential privacy means, imagine two databases, like they are almost identical. So we have database D and D prime, and Alice is not included in D, but included in D prime. And basically, differential privacy dictates that if there's an algorithm that we run on both of these databases, they will give kind of the same results. And this kind of the same result is defined mathematically with a multiplicative factor and an additive factor. So Alice has no incentive not to be included in the database, because no matter what kind of algorithm you run in either the database where Alice is included or the database where Alice is not included, essentially you will get the same output. So Alice's privacy is not harmed. This is just a super intuitive explanation. So we care about, in decentralized applications, about the local model of differential privacy. What is the local model of differential privacy? Let's say they need to release their height. So Alice's height is x1, Bob's height is x2, Carol's height is x3, and they want to release it to an untrusted analyzer. And they release it with a local randomizer. So what they do most of the time is that they take their true height and they will add to it some Laplacian or Gaussian noise. And then the untrusted analyzer, other scientists around the globe, can compute some functions A on top of this randomized data. And we say that an algorithm A satisfies epsilon delta differential privacy in the local model if this function is epsilon differentially private. Unfortunately, fuzzy message detection is not compatible with vanilla differential privacy, because fuzzy message detection is only capable of hiding the presence of a message, but not the absence. So if you want to hide the absence of a message, then it would dictate that we need to have also a false negative rate, but that would contradict correctness. So FMD is not compatible with differential privacy. Therefore, we release this notion and we come up with a new notion of differential privacy called personalized existing edge differential privacy, which is a combination of many previously existing differential privacy notions like edge DP or unbounded DP, where we want to protect the existence of something rather than the value. And this is also a personalized notion of DP, where the protection, the differential privacy protection varies from user to user. So if we assume that the distribution of the messages are independent and identically distributed, then fuzzy message detection satisfies this new, weaker notion of differential privacy. But the more interesting thing, I think, is that fuzzy message detection does satisfy differential privacy for the statistics of the number of incoming messages. So what's the number of incoming messages? So it's in U, and tag U is the number that you downloaded from the number of messages that you downloaded from the server. So you download from the server your true positive messages, and you also download from the server your false positive messages, which follows a binomial distribution. If you zoom out, then you can think of this binomial term as a random Gaussian noise. So essentially, the intuition is that you can think of this term as you would add some Gaussian noise to your incoming messages. And we prove in the paper that indeed fuzzy message detection protects the number of incoming messages in an epsilon delta differential private manner, where delta is this value and epsilon is this value. It is not that important. What is important is that we compute epsilon and delta for specific scenarios, and we found that epsilon is pretty large. Why is it bad? Usually, if epsilon is larger than 1, then the protection of privacy is considered to be weak. So the takeaway message is that differential privacy is obtained, but it only gives some weak notions of privacy. You can also analyze fuzzy message detection from a game theoretic point of view, because you have a lot of users, and each user wants to optimize their privacy. They want privacy, but at the minimum cost possible. So they don't want to download the whole database. They want to minimize the number of messages they retrieve from the database. Let's say the cost of retrieving any message is F. Then the total cost is F times the expected number of messages you download. The cost of privacy breach is L. Then we define the total cost of privacy breach is L times the probability that any of your messages relationship anonymity will be broken. And so basically, these are the two terms of the utility function we are considering, and we are interested in the Nash equilibria of this game, of this relationship anonymity game. And what we found is that, unfortunately, there's only the trivial Nash equilibrium, which corresponds that to the case where all the users define their false positive rate to be 0. So it's like a privacy hell, because there's no privacy protection at all. But we also see the light in the tunnel. The social optimum, if users value their privacy high enough, does correspond to non-trivial Nash equilibrium. So there might be a world where users are incentivized to raise their false positive rate to high enough. We also simulated FMD on real-world networks. So we obtained 2 real-world data sets. One is an instant messaging applications communication graph. The other one is a European Research Institution's email graph. They are all available on our GitHub repo, but we also found it online. So you can play with it if you want. And so basically these graphs consist of nodes, and the nodes represent people who exchange the instant message or an email. And so this is a directed graph. And also we see this is a temporal graph, because for each edge we see the timestamp of the data. So we really know and really see how this network evolved throughout time. What we did that for every recipient, we sampled a false positive rate between 1 and 0. And then for every incoming message in the system, we generated fuzzy edges, fuzzy links, proportional to the false positive rate of the users. So we got a huge graph where there was a lot of true positive edges and many more false positive edges. And we gave it to the server, and now the server ran some statistical tests and needed to decide who is communicating to whom. So the server wanted to break relationship anonymity, and afterwards the server wanted to break temporal detection ambiguity. And the results are, so temporal detection ambiguity is, just to remind you, was the task that the server needed to find out whether in a certain time interval a recipient received a true positive message or not. And as you can see on the right-hand side, temporal detection ambiguity can be broken with high precision and recall. We considered like 2 weeks of data in each cases for both of the data sets. And relationship anonymity is also quite easily broken with precision around 20% and recall with 18% and around 39 or something. So basically the takeaway message, you could say that, well, this precision and recalls are not so high, but this is not something you would expect from a privacy enhancing technology, right? So you don't want to have 20% of probability that your relationship anonymity is broken. And then this is just a more granular way to present the results. On the x-axis, you can see the false positive rate of the recipient. So if the recipient's false positive rate is lower, then the higher the recall will be. And also, the more messages they exchange, the higher the recall is. So let's just conclude. Fuzzy message detection does not satisfy textbook notions of information-theoretic privacy. And our computations and results could help potentially developers and other teams who are thinking about to integrate this privacy enhancing technology to their wallets and anonymous messaging systems. Fuzzy message detection satisfies only weak notions of differential privacy. If there are no altruistic users, then fuzzy message detection incentives seem to be misaligned. And open questions for cryptographers is, can we somehow enhance the cryptographic nature of fuzzy message detection in a way that it will also improve the privacy guarantees we can achieve. We didn't analyze fuzzy message detection from a pan-private point of view. Pan-privacy is when you take into consideration the temporal nature of the stream data, because basically you can think of all these messages as a stream of data, and the server can inspect all this data continuously. So it might be interesting that someone will have a look at it from a pan-privacy point of view. And I think the most interesting or exciting could be to analyze the underlying incentive. So I really expect to see some more game theoretic analysis of fuzzy message detection. For example, computing the price of anarchy or stability would be a nice place to start. Yeah, thanks again to Sarah Jamie Lewis, who gave us the data sets. And thanks, Henry, for chatting with us. And thank you for your attention.
All right, it's time for questions. We can take them on Zoom too. If you want to ask a question from Zoom, turn on your camera, microphone, and just speak. You will appear here. Are there any questions in the poll?
So it seems that the setting that you were presenting for FMD is similar to private information retrieval, where you have the server and the client wants to retrieve the data in an anonymous manner. So could you give an intuition what's the difference between the two?
So like in private information retrieval, just for those of you who don't know, it's a cryptographic protocol where you want to retrieve an information from a database at a given location, but you don't want to disclose to the server at which location that data lies that interests to you. So yeah, fuzzy private message detection is indeed super similar to private information retrieval. But in private information retrieval, you already know that I'm interested in the 10th row of the database. And here you don't have any clue because you were in Mallorca, Ibiza, you took a vacation, you were offline, and you come back to the blockchain and okay, I don't even know the part of the database that is interesting to me. So that's like an even more difficult problem than private information retrieval. That's the crucial difference.
I have a second question. May I? Okay. So in the example that you put before with the senders and the 4 receivers that they are picking different set of messages, you mentioned that I don't know, remember the number slide.
Just a second, it should be here. Maybe this one.
It was with back.
Yes,
this one. So here you mentioned exactly like even recipient D was doing a lot of work for privacy. His or her privacy depending on what the others did before. Right, so what's the history of the behavior of other users in the system before this person? So how is this capturing your notions or in your analysis of privacy? How the behavior of other users in the system is captured in your notion of privacy? Because it seems to me that was user-centric in a sense, but...
Yeah. I mean, it's mostly captured in the game theory part. But not in the differential private setting, and also not in the classical notions of privacy setting. It's really we just focus on a single user. It would be something really interesting to do, but I didn't have time. And I think also the complexity, if you want to analyze it, it really blows up. But Yeah, so Pedro's criticism is valid and legit. We only focused on a single user or a set of users or a pair of users from a privacy point of view. But this toy example shows that you really need to take into consideration all possible recipients, because your privacy guarantees really depend on everyone else. And my intuition is that if you want to do this nicely, then the complexity will just blow up. Would be nice if someone would do that. That would be necessary for any real-world deployment to have a better idea. So we didn't do this in the paper. Like the game theory part is kind of conveys this idea, but that's also not enough.
Oh, maybe your next Auckland paper then.
Would be nice.
Thanks for the talk. I really enjoyed it. I have a question. Often it seemed to appear that the actual privacy you get depends on that parameter P that every user chooses. And like sometimes if all users have like the same one or choose it optimally, you could have good security. In like a secure messaging application, could it not be the actual application which imposes this parameter onto its users?
Yeah, so one of the theorems of the game theory analysis is that if there is a central planner and the central planner imposes like, this is the parameter everyone needs to use, then there's a Nash equilibrium and it corresponds to privacy protection. So in that nice world, we have privacy. Because
initially, like you were saying, there were lots of people that wanted to implement this, like secure messaging apps. And I don't know, I feel like if people download an app, they don't expect to set this parameter. Like you just kind of expect it to be done behind the hood. Yeah,
definitely not a regular WhatsApp user or Telegram user, but maybe, this is far from real world deployment. Obviously, the paper came out in January, February this year. It's just always nice to maybe there's an advanced mode where you can set it because you are privacy cautious or you are altruistic and you want to download the whole database just to help other people's privacy. That's a valid criticism again, that we don't really know how this will be implemented in practice. So maybe there will be a uniform false positive rate for anyone, or maybe the users, most likely I think Silicon Valley developers don't want you to choose your parameters. So most likely it will be implemented in a way that it will be imposed to users. But it seems to be for me that it's a little bit too dictatorship. I don't know. So maybe it will be implemented in a way that it gives the freedom for the users to choose how this parameter is set. But hard to tell.
Thanks for the talk. A bit related to that question. You were mentioning that it is assumed that the server knows P. Right. So could you give intuition why this is the case? Because it seems to me a bit unlike, okay, see, if it's a scenario where you assume that it's kind of synchronized, and then of course it's a reasonable assumption, but like it seems that actually if they would not know, and if you're in a scenario where it's non-synchronized.
So in the threat model, we say that the server knows the false positive rate of each user. Why is this a realistic assumption? Let's say I want to figure out Ignacio's false positive rate. I am the evil server. What can I do? I just send 1,000 messages to Ignacio and test it locally whether it gives a message, gives a match or not. And then it's really easy to figure out like approximately what is Ignacio's false positive rate. So it's known to the server.
Are there any other questions? All right, let's thank the speaker again. Question. Good.
Just a minor question. So I was actually curious if like the number of users that you need to have in the system has to be fixed a priori, or it can change during like time. So if a new user can join after some time.
in our paper, we took it as a fixed value, but obviously the realistic would be that it is like, you don't have like U is a fixed number, but UT that could depend on how users join and leave the system. But again, yeah, we didn't incorporate this into the paper. A more fine-grained analysis would be nice and maybe necessary. Yeah, and also, yeah.
I also expect having a dynamic amount of user could also provide more insecurities, because if a message cannot be received by some user because they're not in the system yet, then that those messages are not meant to be for him. So you have even more information regardless of how which system you're actually using. So thanks for.
Questions, comments, suggestions? All right, let's thank the speaker again.